destination, then fly to home. But if you wanna travel, then go alone. Yeah, what's the point in us if I never know? Yeah, if you're gonna leave, I'ma let you go. Away. I'm tired of the pain. Go away. I'm done with yesterday. Fada, fada. I fell where my demons dwell. My own little nightmare, I call it hell. Oh well, it's time to get back up. Climbing and climbing, I'm done with this ride, is what I tell myself, so I could feel something else. Yeah, I guess I had my bad days, but it doesn't mean I lost my style. Darling, where were you when my heart was on the ground? I thought time would prove that you would stick around. I guess time stood still, a king without his crown. Now I'm breaking and you're faking, girl. You never made a sound. Away. I'm tired of the pain. Go away. I'm done with yesterday. Fada, fada.
Hello, everyone. Hello, and welcome again to another edition of the Azure Cloud Security Meetup group. So, thanks very much for joining us again today. So, I have with me today Mr. Ibrahima. How are you doing, Ibrahima?
Hello, everyone. Thank you, David. I'm finding you.
Yeah, it's been
Very
a
happy
while
to
since
be
we've seen
here.
you. Yeah, you've been very busy, man. You've been a very, very busy man with tons of stuff going on.
No, you're the man which is we busy. Who is busy?
Yeah. So again, glad to have you back. So just to mention to everyone joining us, thanks very much for joining us. So do not worry, we do have Christophe here. So Christophe is in the background, right? It's ready to speak to us on the topic provable cloud security, which itself is it's a very very interesting topic, and I'm looking forward to that. So just a quick reminder, if you're yet to join the Azure Cloud Security Meetup group, the link is in the chat window right now. So go over to that link, click on the link, and make sure that you join the group. That way you can stay in touch with all the updates and all the announcements. Whenever we have a new event or we have a speaking session set up, you will be notified. So, Ibrahim, I think we can go ahead and we can introduce our speaker for today. So let's go ahead and introduce Christophe.
Yes, exactly.
Yeah. So here we go. Hello, Christophe. How are you doing?
Hello, everybody.
Yeah.
I was looking forward to this meeting, to this call, actually, and I hope you are all okay. And not too impressed by the title, Provable Security. I want to make everybody at ease. I'm not going to inundate you with mathematical formula, right? Take it easy. We are going to have a gentle introduction to what it means, where it comes from, and how it can help us for cloud security, especially for IaaS and PaaS. So thanks
Awesome.
a lot, everybody, for being here, and thanks to our facilitators, as you say, David and Ibrahim. Thanks a lot for inviting me and for managing all that for the community. It's great. I see that we have a rock star here who joined us, David Neves. Okay, he was sick, and I was not sure to join. I'm very glad that he is here, and hello to Cedric and the other people that I don't know everybody, but I'm very glad that you could join.
Yeah.
Thanks a lot.
Awesome.
Um,
So without wasting any time, I think we can go ahead and hand over to you. So in case anyone has any questions for Christophe as it goes through the talk, please leave your questions in the chat window. Ibrahima and myself, we're going to manage that. We're going to come on and we're going to read those questions um, to Christophe. So over to you, Christophe. We'll let you
thanks.
carry on with that.
Right. Thank you, David. So a quick introduction, maybe to provability, or maybe to introduction on myself first. For those who don't know me, I work on the cloud security. I've been working for 7 years on the cloud now, and I started working with Azure in 2015. I worked on Azure Firewall and Azure Policy, and I was let's say I contributed a lot to the design of Azure Firewall and Azure Policy back in 2015. So today we are going to talk about an entirely new topic, which is provable security. What is it first? For me, provable security is a way to formally verify and check that the model behaves as one's expect. And maybe it's a little bit abstract, and I like to compare it to maybe software testing, because it's very different from software testing, and you'll see the difference very quickly. When you test software, you know that you add some unit tests to your code, and you try to input a given set of predefined variables into your code, and you run the code, and then you wait for the output, and you compare the output to what you expect. Uh, this is a way of testing stuff, but of course it's very limited. You cannot test everything, of course, when you do a unit test, and some things bad can happen that you cannot catch if you go that way. Proving things is very different, because the ambition of provable security is to make sure that your software works as you expect in any situation. So it means whatever the input variables you put into the model, uh, if the software is well designed, it behaves correctly, it means that you will be the solver, what we call the solver, will be able to tell you if your code is good or bad. It's very appealing, I think, the idea. And it's the reason why it's something that is not so common. I think it's that it has taken a long time, a very long time to mature. And to prepare this call, I have done my homework. I've done a little bit of archaeology, and I tried to understand where provable security comes from, where the solver comes from. And actually, it's pretty old. It came up in the 70s, 50 years ago. So I consulted the research paper back then, and of course, and the more recent paper about the subject. And it all started with the idea of uh, trying to check that a piece of software is. It was very important for some embedded piece of hardware and software to work properly. For instance, you know that in planes you have automated systems that are very mission critical, and the guys back then needed to have an absolute confidence that the hardware was running perfectly right, the ASICs and also the software. So they tried to model and simulate the behavior of the hardware and the software. And so they turned the software and the hardware into like a state machine with input variables. And so the idea was to run through this state machine, which is a kind of graph, and try to analyze every possible input and every possible output. It was pretty easy for tiny pieces of hardware, but quickly it became intractable if you have large pieces of software, like a program or like a very big software. It was completely unmanageable. So they invented a way to overcome this problem somehow through a mechanism that is called abstraction. And it's a very interesting concept, because I will talk a lot about it today. The idea behind abstraction is to simplify and to make something which is completely extremely complex and diverse into something much simpler, but which still captures completely the intent of the software programmer. So the idea behind abstraction is to turn your program into a surjection. It is a mathematical term. I won't use a lot of such terms during the call today, but globally, a surjection is a map kind of function which transforms many inputs, or like a few inputs over a large domain definition, into some outputs over a smaller domain definition. So if you have a lot of variables which are natural numbers, for example, in your program, it will try to group the variables and their domain definition into small buckets. And rather than reason about the whole domain definition of natural numbers, which is huge, it will reason about the packets. I will give you an example, a concrete example. David, can you tell me, I have no idea how many people live in the UK? What's the population, approximately?
And let me bring that up now. So I think there's about 67 million people living
67.
in the UK.
Right,
Yeah.
okay. 67, that's about the same as in France. So 16 million people. Imagine that you want to observe the behavior of 16 million people with a small hardware or VM, a small program running on the VM. It's completely impossible. So what the statisticians do is that they break the population into let's say buckets, and for that they use a surjection. The surjection is, for example, the age of the population. You can say, okay, all the youngsters, the people who are younger than 15 years old, we will put them in a bucket with the young people, and then we would have the bucket with the adults and the bucket with the aged people. So at the start, you had 60 million people to manage. If you use a surjection, you now have only 3 kinds of people. And within a bucket, which is called an equivalence class, all the people are considered the same. You have simplified the model. And it might make sense or not to split the population by age. You can also split it by income. You can split it by religion, by sex. It really depends on what you want to do, but this is really the idea behind the concept of abstraction. It is to make a complex problem simpler. And if you choose the right surjection, you will not lose generality, and you will be able to prove things without losing generality. And if you find something wrong in the abstracting model, like a counterexample, a bug, let's say, it can mean two things. It can mean two things. Sorry. It can mean either that you have a true positive or a false positive. And if it's a true positive, it means that the problem, the bug, is in the original software. If it's a false positive, it's the abstraction which is called an artifact. So it's and all the purpose of the solvers is to try to avoid to have such artifacts, and to when they have a counterexample to propose to you, it has better be a true positive. And there's a lot of research about this kind of optimization of solvers, making them more and more accurate over time. And over the past 15 years, there has been a tremendous increase in the accuracy of the solvers, and that's why we are starting to see much and much solvers around, and people are starting to speak about provable things and automated reasoning. Huge progress, and now the matter is mature enough for us to use. Any question at this time, or something that is not clear?
Not yet. So not
clear?
the questions at the moment. Yeah, it's all good.
That's great. Okay.
Yeah.
Thank
And
you.
just to mention that Christophe also shared a link with me, which I've also put in the chat.
Oh, yes.
Yeah.
Okay, I will talk about the link in just a moment. Thank you, David. So, okay, here we are with those solvers, which are called generally SMT solver. It's also the most powerful solver. So it means satisfiability modulo theory solver. It's like a barbarian word, but it means that what it means, it's an evolved version of the plain satisfiability solver, which reasons about bits. It's so zeros and one. The zeros and one are good for logic, propositional logic problems, but the people over time have managed to extend the expressivity of the solver, so they are more powerful now, and we call them SMT solvers, which are based on SAT basically, but which are much easier for manipulating other things like bits. For example, you can manipulate numbers with bit vectors. You can manipulate objects, abstract constructs with equalities, which is another theory. And most solvers are embedded with several such mechanisms. You can use bit vectors, you can use equalities, you can use uninterpreted functions, you can use sets. Though you have lots of libraries or extensions at your disposal, and you can mix and match them to your liking. So it's really a fantastic tool and very, very powerful. And so what's the link with the cloud security and how we could make the most of it for the cloud? First, let me just give you a short reason why I was interested in provable security first, and you will understand then why it's so useful for cloud security, I think. So in January, I wrote an article on LinkedIn called Introducing Azure Magma. So Azure Magma is not an Azure service. It is a concept that I use because at that time I wanted to have a way to manage network security group at scale on many subscriptions, hundreds of subscriptions. So you can imagine that if you have hundreds of subscriptions, and in each subscription you have several VNets, and in each VNet you have several subnets and lots of NSGs. So that's a lot of NSGs to manage. And when I mean manage, I mean to supervise, to make sure that they are correctly, they're not dangerously set, let's say. So I wanted to have an automated and easy way to check and to have a control over all those multiple NSGs. So I thought of a way of doing it using something that happens to be very close to provable security and to SMT solvers. I didn't know at that time, but I used a surjection actually for that. And I managed to group my NSGs into buckets. So I had several thousands of NSGs, and I had the opportunity to auto-classify them and put them into bad and good buckets, let's say, or unknown NSGs for the ones that couldn't be automatically classified. And the surjection I used was a kind of, well, it was based on equalities. So I was considering NSGs to be equal under certain conditions. Of course, this does not work for every environment. It really depends on the zero trust model you apply in the cloud. Basically, you have two kinds of zero trust. You have identity-based zero trust and network-based zero trust. For example, I know that LinkedIn, the data centers of LinkedIn and all the infrastructure of LinkedIn is heavily network-based. So you have NSGs which are point-to-point, and so you have a lot of NSGs. And in this situation, it's very difficult to apply Azure Magma because it's very hard to tell if two NSGs are similar. For example, just imagine that you want to open a route between one VM and another and allow a VM to reach the SSL port of another VM and on an API, for example. How your solver will be able to tell if such port opening is valid in one situation between VM1 and VM2, and it's dangerous for VM1 and VM3, for example. The solver lacks the semantics to understand what you mean when you block or when you open a port, the port 443 for a given VM. So for network-based security and zero trust, it doesn't work. But for identity-based, you have a limited set of the NSGs eventually that you allow for cross-subscription communication, for example, and you compensate the relatively open environment with a strong identity authentication, authorization, and all that stuff. You know that probably very well. And in this case, it's much easier to find patterns between NSGs and NSG rules, and it's easier to say that two NSGs are equal, even if the rules are different. In fact, you can quickly, I think, from my personal experience, you can quickly find a way to group NSGs together, and equate them, and you put them into equivalence classes. When you put things into equivalence classes, you make a partition of the global set of stuff that you want to manage. So it's very interesting because when you partition something, it means that everything is encompassed, nothing is left apart. There's no outlier. Everything is either in one equivalent class or another, but you have a holistic view of what you want to manage. That's very interesting. And that's the power of the equality theory. It's very simple equality theory. It means A equals B. And the equality relation is reflexive, symmetric, transitive. That's what makes it actually a partition. And it is the simplest mathematical, let's say, function, a binary relation, and very powerful. So with this simple, let's say, this simple function, equality, I managed to automate the classification of thousands of NSG, and it was already a good achievement. But what I say in the article is that I wanted to go a little bit further, because there is, of course, a limit to this exercise, to this drill, because when you do that, at some point you will have to have an understanding of the CIDRs, the IP ranges, because if you don't analyze IP ranges, um, if you consider them just as a string, for example, you will have a very hard time to say that an IP ranges is included into another one, for example. And that's very useful to have this capability for grouping NSGs together. This was the ultimate objective I set myself to find in January. I wanted to have uh, a solver which will be able to analyze the CIDRs and IP ranges to further automate the classification of my NSGs. And so I set out on a journey to find, to think if there was something around that people did, and I noticed that many people worked on solvers and on this kind of problems before me, and I was very happy to know that. And I stumbled on a very brilliant article from Microsoft Research, which is in the link, the link that David mentioned just a few moments ago. It's a wonderful paper which explains exactly right what I was trying to grasp. It explains how Microsoft team in Azure managed to verify and to check that the firewall configurations on Azure is properly set, that there are no dangerous routes which are opened, and it also serves as a what-if simulator, let's say. If they want to make a change on thousands of rules, they have better think twice before making the change, because they can either block everything, or if they can punch a big hole and break their security. And we're talking about, of course, the uh, the backend of Azure. We're not talking about our own subscription, but the backend of Azure itself could be put at risk and could be completely blocked if the firewalls and Microsoft firewall were misconfigured. So they have this. They use the solver both for having a human readable comprehension of thousands or maybe tens of thousands of rules, and they also use the solver to make what-if scenarios. If they change one thing somewhere, what are the consequences in human readable format? That's very interesting, and that's very close to what I wanted to do. The only problem with Seguro is that the algorithm is rather, well, if you're not used to to mathematics, it's complicated. So I spent a long time to understand and reverse engineer the algorithm, and I managed eventually to do it. And I also added some stuff to the algorithm, which is called all BVSAT. It's an algorithm which manipulates multidimensional, let's say, network rules, let's say. And they didn't have, probably they have found this by now because the article is from 2016, but they were missing security tags, network security tags, the one that we have in SSGs, and I wanted to have my solver to be aware of the security tags. So I added this to the algorithm. So I implemented it in Python, and I added security tag support for the solver. So that's where really I dived deep into automated reasoning, and I used that first for managing NSGs at scale, and it was pretty well, even if it's not really production grade now. At least it's very useful for me, because I can, if I want alone, I can manage 1,000 of security groups without having to bother or to ask 10 people to work for me on that subject. Any question at that time? Is that clear? Is it
Yeah,
complicated?
it's
Confused?
going well. So I can see any questions in the chat window at the moment, but it's really going clear. I can see that we have an engaged audience.
Right. Great. Okay. So I'll carry on then. And if I speak too fast or if I speak too Frenchy, and if you don't get me, just raise your hands. Then if I have to rephrase or repeat something or maybe give some examples, I will try to give more examples along the way. Anyway, so okay. So I talked about Seguru, which is it's fabulous, and also I want to talk about AWS, of course, because AWS was actually the cloud provider which sparked my interest in provable security because they've been doing a lot of stuff since a long time. The problem with AWS is that up until very recent times, they didn't communicate a lot about what they did. I mean that, of course, they said, okay, we're doing automated reasoning. They started with Zelkova, an internal tool for doing automated reasoning stuff on S3 buckets. They now have extended their automated reasoning to many other fields, especially IAM. They analyze IAM configuration to find dangerous settings, let's say, through automated reasoning. They also use it for networking. They have a tool, very interesting tool called Tyros. I think it's called Tyros, or Tyros, but I think it's Tyros. It's very useful. It's something that I wanted to do myself, but they did it before me and a long time before me. It's for reachability. Uh, it's very interesting because you can check network reachability between any two assets in AWS, and no matter what stands in between, firewalls, just route tables, proxies, load balancer, transit gateways, you name it. They will without sending any packet on the network, any ping or any whatever, they will be able, by automated reasoning, to tell you if asset A is reachable from asset B on port TCP X or Y. That's really a brilliant tool and a great use case for automated reasoning, I think. So AWS now is communicating a lot about what they do, especially since Werner Vogel wrote a paper on automated reasoning in March. It's called on his blog. It's a fascinating blog of this Amazon CTO. And I strongly invite you to have a look to what he says. It's always very insightful. It's called allthingsdistributed.com. And okay. Lots of insights, very interesting usually. So since he did that, I think that they have published several papers about what they do in Amazon. It's really impressive, and maybe I'll try to talk about it at the end of the talk if we have a moment. So my mentors for Provable Securities are really Microsoft Research for Azure and the Automated Reasoning Group in AWS, which is led by Byron Cook. So he's published several very interesting articles about that. So I spoke a lot of the concept. So now, how can we apply it to cloud security concretely beyond networking, which is already first thing. So if you remember, so a solver is a tool that can be used for, let's say, for solving an open problem. How I see it is you have a problem which is completely open at the beginning, and you add constraint to a problem, and those constraints are like properties that you want your system to meet. And the more constraint you add, the more likely you will be able to frame a problem and to find how would I say it? It's not very clear what I'm saying. So the idea is you want to model a problem with a set of abstract requirements, let's say, which are properties, and those requirements must capture your intent. If you can do that for security, for cloud security control, for example, it means that you have a way to prove that your control works correctly, and the main benefits for that. It's if you automate the control through provable security, you don't have to have guys who are going to run it for you. The people, human error, exists. They can make mistakes. They can miss some things. It's complicated. You have to pay for the guys, and maybe they can do, if they are experts, they may be doing something more interesting for your corporation than just running controls. So if you can run a control in a provable way, you have gained a lot of, you have gained in security, and you have gained in workload and headcounts. Headcounts. So this is, for example, what I did with the hub and spoke pattern. The hub and spoke pattern is, I guess you all know what it means because you are Azure guys, and this pattern is first and foremost an Azure pattern, which was then used in Google and everywhere else. But the hub and spoke pattern is a perfect example that can be turned into a solvable problem. You don't have to use a solver to check that the hub and spoke pattern is valid in your corporation. You can use whitelists, and you can use well, you can turn the hub and spoke problem into a graph. You see your VNets and their peerings together. So you can have a global graph of your organization. You have the hubs and the petals, which are the subscriptions, which are spokes around the hub, and the hubs which are connected together. It makes a very particular graph, which is constructed with a small set of rules. And the graph is a mathematical object, and the generators for this graph are easy to formalize in terms of mathematical expressions. If you can use your own algorithm for doing that, but if you use an SMT solver, the first benefit is that you are forced to implement it the proper way, the mathematical way, I would say. Then you use a solver which is optimized for your problem, and lastly, it is bug free, or at least it should be bug free, error free. You can, of course, have a bug in your properties, the properties you met, but for the hub and spoke pattern, the properties are very simple. You have 3 properties which are really, really simple. I have documented them on the net, and I haven't shared the link today, but you will easily find the PDF online, I guess. So the properties are easy to modelize, and so it's a perfect use case for a solver. For the hub and spoke model, I use two theories, I guess. I use equality theory, and I use uninterpreted functions. So what is interesting to how do you build a cloud security control with a provable solver? You have to rely on something that is very, very useful. It's the ground truth, all the gold mine of information that is available in real time in the backend of your providers. You have 2 ground truths which are very useful in Azure: Azure Resource Graph and Azure Active Directory. AAD, it's for all the roles definition or the airbag model. And Azure Resource Graph, of course, for all the rest, all your resource asset resources. It's real time, it's lightning fast, it's custom-based, it's a marvel. So I use ARG as a ground source, as a snapshot of my environment. And so the ground source are like mathematical axioms. You can inject them into your solver, and the solver will take them for granted because it's the ground truth. It's what you have in your environment. And then, based on this ground source, the solver will be able to derive some information about your environment based on the properties that you want to check. For the hub and spoke properties, you want to check, for example, the hub to hub property, or you want to check the hub to spoke property, or you want to disprove the spoke to spoke property. You don't want any bypass of, you don't want any 2 spokes to be connected together, for example. So the solver will do that for you based on your ground truth. So your properties are theorems that you want to prove, and your ground truth, for example, your VNets peerings, are your actions. And that's basically the building blocks that you need to make a cloud security control which is useful for you, which is automated and unattended and scalable. I will talk about scalability in a moment, because sometimes solvers have some scalability problems that we'll talk about in a minute. But first, I want to check that we don't have any question. No, it's okay.
Not yet. No, no questions at the
I
moment.
hope that I'm not boring everybody, and it's not too abstract. I hope. Okay, let me carry on then. In fact, there are two kinds of, I would say, two kinds of problems that you can solve with an SMT problem in cloud security. You have general, let's say, software coding problems, and you have patterns that you want to prove, like the hub and spoke pattern. So if you want to check the validity of software code, you can do it. Let's say AWS does it, for example, to prove that the keys which are generated by them, so the symmetrical keys, are 265 bits long, for example. It's an example of what you want to check. Usually it's still hard to check a whole program because it's still too complicated to check and too heavy. But for very critical, mission critical software like key generation, for example, it can make a lot of sense to use solvers. And the second kind of things that you can check is like very simple controls, like I said. You can check network-based controls, like the hub and spoke pattern. You can check toxic combination in IAM, for example. I gave a recent example on LinkedIn how I do that, and how I check just-in-time access, and how I cross just-in-time with IAM authorization with provable security to ensure that things behave as expected. And there's a big difference between both approach. It's the same tool. It's a SMT solver in both cases, but you have to be aware that solving problems is a difficult problem, and you have three kinds of programs. In the world, there are three kinds of programs. You have primitive recursive programs, which are the most simple programs you can imagine. They work in deterministic time, and they are sure to halt. They are sure to terminate. You have general recursive programs, which are going to halt. They're guaranteed to halt, but you don't know how long they will take to halt. And you have partial recursive programs, which are the hardest ones. You don't know if they will terminate one day. So SMT solving and solving in general is a partial recursive. The solver might never terminate, never halt. It's related to the famous halting problem of information theory and NP hard problems. You will probably hear that SMT solving is NP hard. For software checking, it is NP hard. For cloud security pattern checking, it is not. It is generally primitive recursive, and it is exactly what you want. And it will scale. It will scale, and it will terminate in time. For most problems you have to solve, like toxic combinations, network reachability, all that kind of stuff is guaranteed to terminate if you implement the properties properly. So the really hard problems are the ones which are related to general software verification. And for that, many progresses are being made by AWS in particular, because they're making use of the cloud and the power of the cloud. NP hard for them is not more, is still an issue, but it's no more a blocker for the problems they need to solve, because they run several thousand solvers in parallel. They shuffle the formulas in the solver, because the order of the formula in a solver normally shouldn't have any impact on the solution, because of course these are mathematical formula. But in terms of the way the solver works, sometimes if you invert two constraints, a solver will terminate or not. It will make all the difference. So they play on that. They use also different kinds of solver and technologies. They use Microsoft Z3, which I am using personally, because I find it very easy to use. It's a Python library, very straightforward. And you have many other solvers like Minisat and all that kind of stuff. And they mix all the solvers together to try to have termination on some very hard problems, which are not directly security related.
Yeah. I'm sorry to interrupt, Christophe. So a question did come in from someone called Doctor. So the question read, how much do you automate things in cloud security? So
with
okay, so
Provable security, I guess.
so it says, how much do you automate things in cloud security?
So not much for now because I have the feeling to be a little bit alone working on the problem, and at the moment I'm trying to make a library of recipes and patterns that could be used and reused for different situations. I'm exploring this for I've been doing that for since January, so it's really recent, and I very much hope that by raising awareness in the community, more people are going to be curious and try to make up their own rules and make up their own controls. So for now, I have I haven't spoken pattern. I have the toxic lock pattern for toxic combos, and I will be doing one or two more controls, one for Kubernetes and one for IAM also for checking group membership so pretty soon. So that will be four, and of course the control NSGs, that's five. It's not much, of course, but at length I hope that we'll have a critical mass of interesting control that we could deploy in the production environments, and I
Hmm.
could all share. And I work. I try also to work with the cloud providers themselves because I've also wrote an article about this. It would be great if the cloud provider would manage this as a service for us, provable security, and we could sort of design our own controls, like Lego bricks, like past services that we assemble together. It would be fantastic if we could have a way to express controls as a maybe as a it would be part of Azure governance, maybe like Azure policy, or along with Azure policy as a complement to Azure policy. It could be a possibility. For now, I have to say that it's not something that is in the pipe. It might be a long-term thing, but at the moment, I'm trying to see if it could be done. AWS on its is using provable security and is offering provable security capabilities to their customer, but that's very indirect. In
Hmm.
Analyzer, for example, they're using it behind the
Yeah.
scenes, but you don't have any way to customize it or to make your own controls. But
Hmm.
maybe it will come soon. I hope it will come sooner or later.
Yeah. That's awesome. And you know what you said, one of the things that you said that sort of like really piqued my interest because it's such a common issues that we see with cloud security, issue around network reachability, right? We talk about it all the time. Someone accidentally exposed something, right? And it's not as if these organizations don't know that they should have policies in place to make things private. It's just somehow, there was like a lapse in judgment somehow. There was a mistake that happened somewhere and that happened, right? Or sometimes it's even difficult, like to your point, to even figure out network reachability. You have proxies, you have load balancers, you have third-party services. So I guess my question is, um, in order for provable cloud security to really like be deliverable, is it something that there needs to be some sort of like open standards that are agreed on by all these different
Yes,
different
you're right, because we are all inventing the wheel, and
Mhm,
it has to be open, it has to be replicable, it has to be shared.
mhm,
The providers are not the only ones who need to, as you said, to troubleshoot reachability.
mhm,
Well, AWS is offering it as a service, but it's completely opaque to us. We don't know what's happening. We just know if it's reachable or not.
mhm.
Um, it's very interesting what you just suggestion to have an open standard would be really, really amazing and fantastic.
Yeah,
Would
nice.
really join forces.
Nice. So there's some other questions that come in. So I guess some of them are around, I guess, people that are looking in the area of cloud security. So Lansana asks, or Joanna Commander asks, what are the steps or skill needed to be a cloud security engineer?
Yeah. So to be a to be a cloud security engineer, I think the first step is to be a cloud security practitioner, and you have to. Okay, yeah, there are certifications, there are online courses, but I think that where for my personal experience, where I learn most is by practicing, experimenting, doing stuff myself on a sandbox subscription or several sandbox subscriptions. Everything which is new. I try to test, maybe not everything because it's too much, but you practice, you try to figure out things yourself, and also by looking at the vulnerabilities. You know that we've had a lot of cloud vulnerabilities over the past year, and there are a lot of insights to be taken from the cloud researchers, the security who found the vulnerabilities, and it gives you some practice and some experience on how the cloud works in the back end. And it's something that is completely different from the online courses and certification that you can have. Not later than yesterday, I looked at books and tutorials on how to learn Azure, and I think they are very, very academic, and it's a really it's a journey through Azure Portal and through concepts which are like nothing less than Azure documentation or AWS documentation. And, okay, it's interesting, but it's not. I don't think this is the way to become an engineer, a security engineer. You have to practice. You have to maybe to work in feature teams which are in production environment with site reliability engineers, sec DevOps teams. You have to practice by learning and by learning from your mistakes and your blunders. I guess probably the best way. It's not always easy to integrate such teams, but that's where you learn most and much more than through online courses, I guess.
Nice. So essentially, what you're saying is, so a cloud security engineer in this day and age needs to think outside the box. That's what I heard you say. Needs to be someone that goes beyond just the basics, the understanding of like other services. You need to probe things, look at things in the back end, learn from other researchers, see what's coming out in terms of all these vulnerabilities, try to figure things out yourself. Nice. Okay, here's another question that came in from Emmanuel. So I'll read that and then I'll let you carry on. So Emmanuel says, what's the roadmap for cloud security engineering? And I guess that's similar to like what
Yes, it's
Joanna
relatively
has.
similar.
Yeah.
You have to know the base and the building block and certification training, and then you have to explore yourself. That's pretty much my advice. It works for me. I don't know if it works for others, but I think it's really, really the best way to learn as far as I'm concerned.
Nice. Okay, so I'll let you carry on. If there's any questions,
Yes,
I'll
I've not much to add. What I wanted to say is, let me check. Yes, a few things. When a solver runs, it will, if it terminates, it will say, okay, your problem is satisfiable or not satisfiable. If it's satisfiable, it means that it found a solution to your problem. What is a solution to a problem? It really depends on the context. The solution can be an anomaly, so a counterexample to what you expect, or it can be something that is positive. And so there is no direct correlation between the answer of a solver and the fact that it's a security risk or not. You have several ways to approach security. Sometimes your solver, you won't have any other option than to have an unsatisfiable answer to a cloud control. It's a bit frustrating because an unsatisfiable answer to cloud control means that the solver didn't find anything interesting, so it doesn't report anything. It means that everything is okay. Or sometimes it's more interestingly, but you don't always have the choice. You have to be very inventive, but it's not always possible. You are hunting for satisfiable answers, which means there's a very juicy ones, the things that you didn't expect, and you say, "Oh wow, I didn't anticipate this." There is a problem in the caveat in the design of my stuff, and I didn't anticipate that. This happened to me with the NSGs, for example. The solver found NSGs that were open that I didn't anticipate, and also it found several toxic combinations that I didn't imagine was in some of my environment. So I was very amazed, and I think it's impressed by the solver, and it encouraged me investigating further and making more controls. So that's what I wanted to say about satisfiability. And the last thing I wanted to talk about is the little announcement. I want to make an announcement today since I'm here. I will very shortly release not really a control, but let's say something to learn automated reasoning and to understand maybe better automated reasoning. It is a Kubernetes-like orchestrator, which is based on Provable security. So this it's a tiny orchestrators which try to place containers on nodes, on Kubernetes nodes, based on constraints. So we have two types of constraints. We have affinities and anti-affinities, anti-affinities. These are, let's say, I would say, geographical constraints, and also node size constraints, because every single node has a maximum capability depending on the amount of hardware and software it has. So this orchestrator, I think, is a great tool to learn automated reasoning in a concrete way, because it solves problems. It tries to find a satisfiable answer to containers placement on a cluster. And it uses bit vectors to check nodes capabilities, and it uses equalities to check affinities and anti-affinities. So I will publish a link very shortly on GitHub and on LinkedIn, so that I will share the public domain version of the tiny orchestrator, so that everybody can have a look. If you want, you can have a look, you can contribute, you can fix bugs because there are some, but it's really a tool that I want to share for educational purposes. Of course, it's not production ready, but it's something that really maybe helps to get a clear answer, or maybe a better view of what solvable problems can be. And I think that this problem is more complicated than the problem I mentioned earlier, and the solver is not guaranteed to terminate in some situation, because it's NP hard, as I mentioned. But at least it tries to find the best solutions according to your constraint, and I think it's an interesting use case for SMT solving. That's all that I had in the pipe for today. Of course, I'm free to answer any more questions. Or I hope you're not completely bored or impressed by what I just said. The more people work into these domains, I think the more we will all benefit.
I think that's awesome. And again, I've put Christophe's LinkedIn profile, a link to Christophe's LinkedIn profile in the chat window. If you're not yet following Christophe, please ensure you do so. Christophe has amazing um, newsletter that you release where you talk about some of your thoughts around cloud security, which I highly recommend that you follow again Christophe's LinkedIn profile, and you also subscribe to the newsletter so you can get like a lot of these updates and amazing analysis that comes out from Christophe almost every week, I think. So it's one
Thank
of
you
the
so
things that I
much.
look forward to.
Thank
Yeah.
you.
Yeah. So someone had asked a question. So I think that we can take like maybe just one or a few more questions. So Emmanuel says, what are the use cases for security issues? I'm guessing that you're talking about provable security, Emmanuel, in terms of some of the use cases. Um,
For example, if we talk about, let's say, the hub and spoke pattern, uh, in some cases, the solver will, hopefully, the solver is holistic, as I said in the introduction. So it means that it will always tell you if your hub and spoke pattern is right or wrong. That's the power of automation. So
yeah.
if it finds a satisfiable answer, it means that it will find, for example, it will disprove your configuration. It will say, hey, those two subscriptions are connected together. They shouldn't.
Mm,
Or maybe,
mm,
oh, there's this standalone VNet. It's not connected. It's just dangling. It's just not connected to anything. It should. Stuff like that. This is the kind of stuff a solver will find for you very easily. And it will also find maybe NSGs that are not classified yet, or which have not been able to, the solver has not been able to say, oh, it's a good NSG or it's a dangerous NSG, something I don't know, I've never encountered before. I need human intervention to help me.
mm,
And and so in this case, you will have the humans that will have to to tell the solver, okay, this one is good or this one is bad, but this kind of stuff. And also, let me just stress that there is another very interesting interest about interesting. Sorry, there is a very solvers are very powerful also for what if scenarios. As I said in the introduction, if you want to simulate something on a complex environment, you
mm,
can do a semantic difference between what you had before and what you will have if you do the change. So it's very in a human readable format generally. So So for complex systems, it's also very useful to have what-if scenarios and to anticipate potential bugs or potential problems.
That's awesome. So, final question for me, Christophe. Should we look forward to a newsletter on Provable security and a release of some of the? I know you announced the Kubernetes Light Orchestrator today. So, should we look forward to a newsletter on Provable Cloud Security very soon?
I have made several already, so
Yeah.
maybe not in the foreseeable future. I will work on a newsletter on maybe confidential computing because of the recent announcement.
Yeah.
I have also talked about a link between quantum computing and provable security recently. So I try also to make links between those and apparently related domains, but there are many links. You can prove things with quantum computers. Satisfiability is something that is really amenable to quantum computing. So I have produced some stuff about that. What I will probably try to do in the next couple of months is publish more recipes. I was saying that I want a critical mass of controls, so I will try to keep publishing recipes that could be concretely used for a concrete use case in public cloud. So because I have only 4 or 5 at the moment, so it's not enough. That's what I plan to do in the next months.
Nice. Christophe, it's always a pleasure to hear you. I mean, there's lots of thoughts and ideas and stuff that really come to me from this presentation. I'm sure that we'll carry on with some of those conversations.
Yes.
It's just a very, very interesting area. I've seen different companies try to tackle that challenge. In terms of trying to handle things like true network exposure, toxic IAM combinations like you talked about, and trying to leverage some of the ideas behind things like automated reasoning. And again, it's just very interesting always to hear you. So thanks very much again
for hosting and for bearing with me. Thanks a lot.
It's always a pleasure. So thanks very much again, everyone, for joining us. Really appreciate you taking time to hear out. Again, if you're yet to, make sure you follow Christophe on LinkedIn. Make sure that you follow the Communities Meetup channel. So we look forward to seeing you next time. So Ibrahim, any last words that you have before we say bye to the people?
Maybe Christophe just publish some information for newbies.
Yeah.
Yeah.
It will be helpful.
Okay, right. I'll try to. Okay.
Awesome. So thanks very much again, Christophe.
Thanks a lot for your time. Thanks so much, everybody.
Everyone, thanks very much for joining us. Do have a lovely rest of the day. So bye for now.
Bye-bye.
Thank you all. Bye. Ciao, ciao.